Welcome back, everyone. Today, we're taking on an absolute heavyweight of the skies. We are talking about the incredible engineering that lets pilots literally tame the 10-ton twin-rotor beast known as the CH-47 Chinook. This isn't just your standard single-rotor chopper. With counter-rotating tandem rotors and over 10,000 combined horsepower, it's a whole different animal. And today, we're going to demystify exactly how it all works. Okay, let's dive right in. Here's our flight plan for this explainer. First, we'll step inside the cockpit. Then we'll break down the primary helicopter flight controls. After that, we'll look at the Stability Augmentation System, and finally, the Speed Trim System. All right, Section 1. Inside the Chinook cockpit, also known as the pilot's office.
Now what's really interesting here is the setup. Just imagine stepping right into the pilot's seat of this massive machine. You've got the pilot sitting on the right, the co-pilot on the left, but right down the middle, that's a shared center console packed with crucial engine, transmission, and fuel instruments. Because flying this thing takes such intense coordination, the whole layout is specifically designed so either pilot can effortlessly take control and monitor the helicopter's vital signs in a split second.
You know, modern Chinooks have definitely had some massive upgrades since they first rolled out in 1961. Today, pilots process a staggering amount of information across the battle space using multifunction displays, or MFDs, which map all that mission data right in front of them. And the communication setup? It's an absolute powerhouse. Nestled right down there in the lower console between the seats is a crazy 7-radio array. We're talking interphone, FM, VHF, UHF, the whole shebang. It ensures they can talk to ground troops, command centers, and escort aircraft, like Apaches, literally all at the same time.
Moving right along to Section 2, Primary Helicopter Flight Controls, mastering those tandem rotors.
So let's move from what the pilot sees to what they actually do with their hands and feet. Flying the Chinook really comes down to a triad of manual flight controls that give the pilot command over the 10,000 horsepower generated by those twin-Lycoming engines. First up, the thrust control, which is basically the Chinook's version of a collective, and that handles vertical lift. Second, you have the Cyclic stick for pitching forward and back or rolling side to side. And third, the directional pedals for yaw. Let's break down exactly how these mechanically manipulate the blades.
It's super cool that contrasts these two fundamental movements. When the pilot pulls up on the thrust control, it increases the pitch on all 6 rotary wing blades at the exact same time. 3 up front, 3 in the back. That's what gives you your vertical lift. But when you push the cyclic stick forward, it creates this thing called differential thrust. Basically, it decreases thrust on the front rotor and increases it on the rear rotor. This tilts the entire aircraft nose down, pushing it forward through the air.
Now, let's talk about yaw. Spinning the nose of the aircraft left or right. Standard helicopters, they just use a tail rotor for this. But the Chinook? It doesn't even have a tail rotor. Because the front and rear main rotors actually spin in opposite directions, their rotational torque naturally cancels out. So to spin this absolute beast, the Chinook relies on a completely different and frankly brilliant aerodynamic trick.
And this brilliantly illustrates how it works. When the pilot steps on the left directional pedal, the mechanical linkages tilt the plane of rotation for the front rotor down to the left. At the exact same time, the rear rotor's plane tilts down to the right. So by pushing the front of the aircraft one way and the back of the aircraft the other way, this massive 52-foot fuselage can literally spin on a dime. It's just a flawless hovering turnaround the vertical axis.
All right, Section 3, the Stability Augmentation System, or your electronic co-pilot.
We've covered the manual flying, but now it's time to talk about the invisible systems that keep this 60-foot-wide rotor system from just shaking itself apart. Enter the Stability Augmentation System, or SAS for short. The SAS is essentially an instantaneous electronic dampener. Using rate gyros, it senses any abrupt change in the helicopter's attitude, like, say, a sudden gust of wind, and instantly fires off signals to correct it. It completely eliminates all those tiny, exhausting corrective movements the pilot would normally have to make. In fact, it often stabilizes the aircraft before the human pilot even realizes the wind shifted.
Now, I want to highlight this absolutely fascinating engineering quirk straight from the aircraft's manual. The dual hydraulic cylinders doing the heavy lifting are so incredibly powerful that the pilot actually wouldn't feel any resistance when moving the controls, none. So to fix this, engineers literally installed spring assemblies and magnetic brakes to synthesize an artificial feel. They have to fake the physical resistance so the pilot intuitively knows how hard they're pushing against the air. How crazy is that?
When you trace how the SAS intercepts the pitch, roll, and yaw signals, there's one design feature that is absolutely crucial to understand. The SAS only has 50% authority. What does that mean? Well, it can extend or retract linkages to dampen motion, but if a correction requires more than 50% of the control's range, the pilot has to step in. It assists perfectly, for sure, but it is hard-coded to always allow the human pilot to override the computer. Let's move to Section 4 and see how this all builds together with the speed trim system, which is all about leveling the fuselage.
This final piece of the puzzle is all about managing the extreme physics of high-speed forward flight. You see, the Chinook is fast. We're talking speeds approaching 200 miles per hour. At those speeds, the aerodynamic forces are constantly trying to pitch the nose of the helicopter up. If a pilot had to rely purely on manual cyclic adjustments, they'd have to physically hold the stick forward against this immense pressure for the entire flight. That would be completely exhausting. So the solution is the automatic speed trim system, which electronically does the heavy lifting to maintain a level fuselage.
Here's how it actually pulls that off. The speed trim system is constantly pulling airspeed data from the pitot-static system. As the aircraft flies faster, the system generates an electronic signal that automatically adjusts the tilt of both rotary wings. It effectively trims the rotors to keep the fuselage perfectly level, even at really high speeds. It even removes some of that differential collective pitch we talked about earlier, giving the pilot a comfortable positive stick gradient. It basically wrestles the brute force aerodynamics so the pilot can just focus on the mission.
So, what does this all mean? Well, it brings us to a final thought for this explainer. With twin engines generating over 10,000 horsepower, dual rotors spanning 100 feet, and mechanical computers like the SAS and speed trim making micro adjustments every single second, who is really flying the Chinook? Is it the pilot or the machine? Ultimately, it's this masterful synergy of human intuition and mechanical automation. And it hasn't fundamentally changed since 1961 because, simply put, it hits the nail on the head as the absolute apex of heavy lift aeronautical design. Thank you guys so much for joining me on this deep dive into the CH-47 cockpit, and I hope this leaves you eager to explore more incredible aviation engineering.